Hello, this is Teacher Fabi, and I'll be recording my lessons that were presented to my classes before the pandemic. During this pandemic, I was thinking how I could present these lessons so that somehow it could help students who are taking these classes understand the concepts in science, particularly in chemistry. I'll be uploading this in my YouTube channel, and you can access and you can listen to the discussion for each of the lessons that I have. The lessons will start from the simplest ones to the most complex as they are presented in the course outline in the third year high school or grade 9. But of course, other students who may want to access this and learn from this are welcome to learn from these presentations. So I hope you will enjoy the presentations. Thank you. So for today, we are going to start with analyzing data, particularly units and measurements. Chemists use an internationally recognized system of units to communicate their findings. In this lesson, we have two objectives, and that is to be able to identify the international unit system and to familiarize with base units and SI prefixes. So, SI means System International. And for this lesson, I would like to use this picture as our springboard. Um, you're familiar with the different sizes of drinks in fast food chains, such as McDonald's, right? So let's take a look at the different sizes in the US in terms of their soft drinks. So they have the small, which is 16 ounces, medium 21 ounces, and large 30 ounces. In Australia, they seem to have also three different sizes. But if you see and compare it with the ones in the U.S., um, it seems that they have the same small size, but their medium is a little smaller than the medium of the U.S. and it's just a bit, taller than the small. And for the large one, it's still a little smaller compared to the 30 ounces of that in America. The same is true with the ones in Hong Kong. It seems that Australia and Hong Kong have the same type of sizes. Okay, and in Japan, it shows here that they only have two sizes. Um, Rather, the Japanese large is being compared to the USA's 1.5 large. Okay, so it says here 1.5 times bigger than the large of Japan. So, what um, what implication do we get from this picture? It's just like when you go to different countries, it seems that they have their own definition of the small, medium, and the large sizes, isn't it? So, in other words, it seems that there is no exact standard that the different countries are using. So maybe the next time you visit McDonald's here in the Philippines, maybe you can also compare the different sizes of their soft drinks. Okay, so let's move on to the next slide. Here's another picture just showing that in the US, the the cup that looks just the same as in Canada and Singapore would be um, regarded as, in the US, it's less than the one in Canada and equal to the one in Singapore. So, still, it seems that these three countries are using different standards when it comes to uh, the amount of the soft drinks that they put in those cups, although they would look the same. But well, the symbols less than and equal would mean that they are not following exactly the same standard. Okay, so um, here's another picture. So it says here 10.1 fluid ounce or 299 milliliters of water. So you can see that there is a specific unit that is used to measure the water that is in this container. So that's the amount, or that's the standard that was used. And who among you are familiar with this? So this is the sundial, and um, in the ancient times, they didn't have clocks or watches that uh, we use in today's time. Um, they used to um, use this sundial, and sundial is uh, dependent on the position of the sun, right? So um, they try uh, to tell the time in terms of the position of the sun, therefore the shadow that the sundial would create. Okay, so that's how the people in the old times would tell the time. Unlike now, we have the clocks, we have the watches, and you know how a clock would look like. So when you say 1 o'clock, then you should know where the short hand and the long hand of the clock would be pointing. But in this case, if you look at the sundial, there is no short hand, there is no long hand, but it's actually the shadow, the size and the length of the shadow that would tell the time to people of the ancient times. And also, if you're familiar with this is an hourglass, and well, it could tell you like when both sides have this um, it's a container with well, sand inside, and you you would need to first collect all of the sand there in one side, and when you turn it upside down, that would indicate that that would be the start of your timing. So if your hourglass is saying that when the all of the sand would be already in the other side of the hourglass, then it would be, let's say, for example, a minute or 5 minutes. So that's the use of the hourglass, right? So this is also this was also used before. Okay, so these are the primitive ways to take measurements. So we have, for example, for distance, they would only use to count the steps that they would make. And for the time, I am, as I've mentioned, the sundial or hourglass filled with sand. And for the length, from the elbow to the tip of the middle finger. Okay, so they used to measure the length whatever that would be, whether it is a foot or a yard, then it would be from the elbow to the tip of the middle finger, or from the tip of the middle finger to the middle of the chest. So that's how they used to measure. But what seems to be the problem with this type of with this ways of measuring? Um, well, first and foremost, the measurement would not be accurate, right? So, for example, for counting steps, what if the person would be the person's stride or the steps would be bigger than the others? Then that would already mean a discrepancy in the distance. And then for the time, not all people would be able to accurately measure or um, determine the shallow that is created by the sundial, or maybe the hourglass would also be erroneous and would not be accurate. And for the length from the elbow to the tip of the middle finger, again, the the measurement it varies from person to person, right? There would be some uh, arm that would be longer than others. So when you say let's measure the length of this cloth using the this from the tip of the middle finger to the elbow, then it will vary from person to person. So in order to solve this problem, then they have created the System International de Units. In 1960, an international committee of scientists met to update the existing metric system. Okay, so SI units. So for the SI base units, we have for length, we have the meter, and the symbol for that would be M. Mass would be a kilogram, kg, time, second, S, electric current, ampere, A, capital letter A. Thermodynamic temperature would be Kelvin, capital letter K. Amount of substance, mole, MOL. Luminous intensity, candela, or CD. So, and for just to introduce the some of the factors and names and their symbols, because here you will be dealing with either a small number or a big number. So you have this table. You can go back to this if you will need this later on. So let's say, for example, 10 to the 24th would be iota, y, 10 to the 21st, zeta, z, 10 to the 18th, exa, e, and so on and so forth. So that's arranged from the biggest to the smallest. Yocto being the smallest, 10 to the negative 24th, with the symbol small letter y. So let's take a look at the kilogram. So what is the standard kilogram? Okay, so nowadays, let's say you go to the market and you would say, I want to buy a kilo of rice. So what does the seller would do? Just take some container and then weigh the rice on a weighing scale that says 1 kilogram, right? But what is really a 1 kilogram? So the kilogram is officially defined by a lump of metal stored in a vault in France for more than 120 years under the International System of Units, or SI. So the international prototype of a kilogram, as you can see in the picture, it was manufactured in 1889. It is made up of 90% platinum and 10% iridium. It is kept in a vault at the International Bureau of Weights and Measures, BIPM, along with 6 official copies. the basis of more than 80 copies distributed around the world as national prototypes. It is steam cleaned under strict guidelines on a regular basis, and the last remaining base unit measured against a specific material artifact. So it says there the chunk of metal is under triple lock and key in Sèvres, France. Okay, so to avoid getting uh, lost or taken by anyone, then they have placed this under triple lock and key. Okay, just to make sure that the standard for the kilogram that we are using nowadays is kept safely in France. Okay, so that's how they have created the kilogram. Okay, and it is from this prototype. And so another common measurement that we usually encounter every day would be the meter. So what is a meter? It is 1/10 million of the distance from the North Pole to the equator. 1/10 million of the distance from the North Pole to the equator. Distance between two fine lines engraved near the ends of a platinum iridium bar. It is also regarded as 1,650,763.73 wavelengths of a particular orange-red light emitted by atoms of krypton 86, and the length of a path traveled by light in a vacuum during a time interval of 1/299,792,458 of a second. So that's the history of the meter. So nowadays we have the meter stick. If you say, I want to buy 5 meters of that cloth, you simply get a meter stick and start measuring, right? But where did that meter and how did it come about? And this is how it came about, okay? So this slide shows you the definition of the meter. And another one is the temperature. So temperature, what is temperature? It is just the measurement of how hot or cold the object is. And it is a quantitative measurement of the average kinetic energy of the particles that make up an object. It's something to do with the kinetic energy. So all of the objects that we have around us, these are made up of particles, and the particles are actually like moving. Okay, even in solid matter, yes, they are vibrating, and the average kinetic energy of the particles that make up an object is called the temperature. So as the particle motion in an object increases, so does the temperature of the object. All right, so that's another measurement that is widely used nowadays. So let's say, for example, you have a fever. You just take your thermometer and then read the temperature reading from there, right? But what is it? How did it come about? Okay, so and what are the different scales of our temperature? So, well, one of these would be the Fahrenheit. But of course, as you can see, this is a perfume, right? It's a scent, very popular scent that is being sold in the market. Fahrenheit by Dior. But well, this is named after that, but this is not actually the temperature that I am referring to here. So this slide shows the three scales of the temperature. Of the first one is the Kelvin, and then the Celsius or the centigrade, and the third one is the Fahrenheit scale. So you can see, as you can see, you can compare. You can compare. Let's take a look at the Celsius, the middle one. So the boiling point of water, is 100 degrees Celsius, and it is equivalent to 212 degrees Fahrenheit. And for Kelvin, it is 373. And if you go to the middle, there is that 0 degrees, which is the freezing point, and that is equivalent to 32 degrees. 32 degrees Fahrenheit and 273 degrees Kelvin. Okay, so how do you convert one temperature to another? So this is how you convert from Fahrenheit to Celsius formula. If you're looking for Fahrenheit and if you're given the Celsius, you simply multiply the Celsius reading by 9/5, and then you add 32, and you get the Fahrenheit. And from Fahrenheit to Celsius, you have to subtract 32 from Fahrenheit and then multiply it by 5/9, and you get the Celsius reading. Okay. And how to convert Celsius to Kelvin? This will be very, very useful when you will be dealing with gases. The different gas laws would be using the Kelvin. So in the problem, if you're given the Celsius scale, all you have to do is convert everything to Kelvin before you start your calculations. So let's say, for example, Celsius. If you're given the Celsius, you always have to add 273 to that Celsius reading to get the Kelvin. Okay, so for example, if you're given 10 degrees Celsius, what will be the equivalent reading in Kelvin? So that's 10 plus 273, that becomes 283. Okay, so from this basic SI units, we also have the derived units. What are derived units? A unit that is defined by a combination of base units. So these are examples of the derived units. So we have under quantity, and you have the definition and derived unit or name. So let's say, for example, for area. Area is a derived unit, and it is defined as length times length. And the unit would be meter squared. For volume, it's area times length. Area times length. So you have already the area, which is length times length, or length times width times height, would be in cubic meters, or m to the third. And then you have speed, you have distance over unit time, meter per second. Density is mass over unit volume, kilogram per meter cube. Acceleration, change in speed over unit time. Force, mass times acceleration. Energy, force times distance. And pressure, force divided by unit area. And you can go back to this table if you need this in your computations later on. This is another similar slide, but there are some others like the symbol. The symbol is included here. So area is A, volume is V, speed, velocity would be small letter V, acceleration is small letter A, density is rho, and then refractive index is N. Okay, so and then you have the name and the symbols. Now, so these are some of the conversions that you will use later on. Okay, for example, for weight, you have 1 ton is equal to 1,000 kilograms. A kilogram is 1,000 grams, and a gram is 1,000 milligrams. So another derived unit here would be a liter. A liter is equal to 1 cubic decimeter, and it is about the same volume as 1 quart. Okay, and for time conversions, we have you're familiar with this. One week has 7 days, one day has 24 hours, 1 hour has 60 minutes, 1 minute has 60 seconds. And for 1 year, you will have 365 days, equivalent to 52 weeks or 12 months. So, and you can see, for example, you're converting a something big to a small one. So big to small, we have to multiply. And if it is from the small, for example, minutes to hours, then it will be divide. And so these are some of the converted units. 9 hours would be 540 minutes. 18 hours would be 1080 minutes. 16 minutes, 960 seconds. 10 minutes, 600 seconds. 2 minutes, 120 seconds. And 2 hours is 120 minutes. So in my classes before, I would give them some exercises, and so you can also practice doing this. And you can go back to the slides that we have discussed. Now, there's another unit or entity that we encounter usually, and this is density. So the symbol for this is like a small p, but it's actually a Greek letter that is represented by the Greek rho, rho. So it's like a small p is equal to mass over volume, and um, question is, why does density vary? The density of the material depends on two things: the individual mass of each atom or molecule and how tightly the atoms are packed. So if you look at the high density material, the particles are packed together and tightly, and there's not much space in between. While the low density ones, particles are loosely packed together and more spaced in between. So um, when you identify, how do you identify the tool for the property that you are measuring? So, for example, for mass, you can use the triple beam balance. For the length, you can use ruler or tape measure. And for the volume, you can use graduated cylinder. Okay, and some other lab apparatus that you can have in the laboratory. And simple comparison of densities. Um, you have that object there, which is quite compact, okay, and solid, and while the other one is a sponge and squeezable, right? And the particles would not be as compact. That's the first one. Okay. These exercises are related to the density that we discussed, so you can also try to practice using this formula. Okay, and in my classes, I would usually also give homework, but I guess you can use other textbooks to look for other problems on densities. Okay, and so what is the implication of having a standard? That is the question that I want to ask you before we end the lesson. What is the implication of having a standard? And what happens if there was no standard way of measuring things? So when you have a standard, um, obviously everyone will need to follow that standard, right? So uh, it's not only some, but everyone. So nowadays, when we say 1 kilogram, you know how heavy is a kilogram and how long is a meter. And in terms of the of telling time, um, what time um, it is using a specific standard. So having a standard is very important in our daily lives, right? If there was no standard way of measuring things, then what do you think would happen? There will be chaos. There will be confusions. Okay, so like when you go to the market and there is no standard for a kilogram, and each of the and everyone would have a different way of measuring a kilogram, then it's definitely going to be chaotic. And it is going to be a, a venue for people to fight. Okay, because some would say that no, this is my standard of a kilogram or a meter, and the other would say no, I think my standard is correct, not yours. So it's going to be a venue for fighting. And in order for this to be avoided, then uh, they um, they have thought of having a specific standard that everyone would need to use. Okay, so that of course our life, our daily encounter with measuring things would not be uh, difficult and would not be chaotic anymore. Okay, so I hope you have learned something from our lesson, and you can always go back to the slides that I have presented here in order to recall what I have discussed, and you can write down your comments and you can ask questions, and I will try to answer those questions. Thank you, and I hope that you learned something from this.